At this point, you guys are champions of covalence. You know their geometries, you know the polarities, you know the shapes, which is geometries. You know how to name them, you know how to write their formulas. We now know how to draw an ionic compound and the differences between ionics and covalence. What we really need to do now is focus on something that I cannot overstress the importance of, which is learning how to name ionics and, most importantly, how to write the formulas from their names. Now, if I was going to pick one thing from the first semester that would be the most important, that would have the largest impact on the rest of this school year, both semesters, I would probably have to pick this one thing: your ability to name and write the formulas of covalence. Excuse me, ionics, of ionics. We're going to be doing this from now through the end of the school year. In every single unit, you're going to have to be or be held responsible to write the formulas for ionics. Some people really struggle with it, so I'm going to go through this slowly, make sure you guys can understand it. But this is absolutely important for you guys to fully understand, okay? You guys know that when we're naming covalents, we use the prefixes, the Greek prefixes, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and of course deca. We do not use any prefixes whatsoever in covalence. I keep saying that. Excuse me, guys. My mind is in covalence. And we do not use those in ionics. I'm sorry, guys. Um, so whenever you see a prefix, mono this, tri, tetra that, that is a clue already that, of course, you're talking about a covalent. In ionics, we don't use those at all, okay? So like it says here, no superscripts or charges in the formula and no prefixes. What we're going to do, guys, is we're going to do a process or a technique that we basically call crisscross. We're going to do a crisscross of the charges. So what I mean by that is, let's just do a very quick example. Say we had aluminum, which has a +3 charge, and oxygen with a -2 charge. Okay, if that's the case, if that's the compound we have called aluminum oxide, in our final formula, we're not going to have any superscripts. So those +3 and the -2 need to disappear. We're also not going to have any charges. So that means there is no positive and no negative being shown. So we're going to do a little crisscross where we move those down. So our final formula would be Al, not 3, but 2, then O, and then we're going to take the 3 from the aluminum and move it down here. Again, notice I dropped off the positive negatives. But what that basically tells you guys, as you hopefully know by now, with the pattern that I tried to show you guys, the aluminum has a +3 because it has 3 valence electrons that it wants to get rid of. The oxygen has a -2 because it needs 2 more negatively charged electrons to fill its octet. So aluminum has 3, oxygen needs 2. So in order to satisfy both, where the aluminum loses everything and the oxygen gains what it needs, you need to do the exact opposite and you switch them. You're going to need 2 aluminums to satisfy and fill 3 different oxygen atoms. That's the way it's always going to work. If the charge is 3 and 2, then it becomes Al2O3. And that's true for anything we do in this thing, in these ionics. So as long as you know the charges from the column that it's in within the periodic table, then you know how to do ionics. It's really not that difficult. Some people just seem to make it harder than it should be. To continue on in the notes, it says in an ionic compound, the substance with a positive oxidation number or charge is written first, and the substance with the negative oxidation number or charge is, ooh, wow, negation. That's not even a word. Negative oxidation number is written last. So basically, it's always going to be in a positive, negative order. The example I have up at the top of the screen is Al2O3. Again, notice at the very top here that your aluminum is the positive, the oxygen is the negative. It is positive followed by the negative. So it's always going to be metal followed by non-metal. For example, magnesium chloride is MgCl2. If I was going to do strontium, let's say phosphide, that would be an example there. Okay, now why that is the case is because if I was going to do, let me use a different color. So magnesium is a +2 charge, chlorine is a -1. Strontium is in the second column, so it's a +2. Phosphorus is a -3. Again, if you guys notice the pattern, I'm going to take that down there. I'm going to take that down there. This goes down here. This goes down there. Notice I did not write a 1 over here because if you have, we don't say Mg1 because if you wrote Mg, clearly you already have a magnesium, right? That's a little redundant to say magnesium 1. Magnesium is one magnesium. If it's more than one magnesium, we would say magnesium 2 or Mg3 or Mg4, Mg5. That's the way it always works. A couple more examples. We're going to have, say, we have calcium nitride, which is going to be something very similar to what I just showed you, or lithium oxide. Okay, so the way this is going to work, this is going to be a 3, this is going to be a 2, and that's going to be a 2. Okay, how do I know that? Because the charges for calcium in the second column is a +2. The charge for nitrogen in the fifth column is a -3. Lithium is an alkali metal, it's a +1. And oxygen is a -2. Therefore, again, if I follow my pattern, this 3 moves down there, that 2 moves down there. This 2 moves down there, that 1 is not shown because, again, it is an assumed 1 oxygen. So this is the way we write the formulas for ionics. It's always the metal first, magnesium, strontium, calcium, lithium, followed by the nonmetals, in this case, chlorine, phosphorus, nitrogen, and oxygen. Okay, so ionics are composed of positive metal ions, or in this case, something called an ammonium ion, NH4 with a +1 charge. We'll talk about that in a little bit, maybe in the next video. And negative nonmetal ions, or a polyatomic ion, which again, I'll talk about later. An example would be this right here. That is a polyatomic. They are held together, of course, ionics I'm talking about, by the positive and negative electrostatic force between the charged ions. Because the opposite charges attract, they are going to be bound together quite strongly, and that is much, much stronger than the covalents that share their electrons. Okay, so ionic formulas are written basically in the lowest ratio, in the lowest whole number ratio. So what I mean by that is, let's say we have magnesium and oxygen, magnesium oxide. Okay, now the charges for magnesium oxide, Mg is +2, O is -2. Again, that's all based on the periodic table. So I do not do Mg2O2. Okay, we don't do that because even though, again, if I follow the proper technique and I do my crisscross and that moves down there and that moves down there, we do not write Mg2O2 because 2 magnesiums for every 2 oxygens is the same thing as 1 magnesium for every 1 oxygen, which is the exact same thing as 3 magnesiums for 3 oxygens or 4 magnesiums for 4 oxygens. It's just like in math when you have a fraction. We don't say 5/5 or 1,000/1,000. All of those are equal to basically 1 because you're going to reduce it all the way down. It's the exact same thing in chemistry. 2 magnesiums and 2 oxygens is the same exact thing as 1 magnesium and 1 oxygen, because remember, this is a crystal structure of repeating patterns of magnesium, oxide, magnesium, oxide, magnesium, oxide, positive, negative, positive, negative, positive, negative. It could very well, if we have a pure chunk of magnesium oxide, it could be magnesium 10,000, oxygen 10,000. We don't know, but it's always going to be a 1-to-1 ratio. So we show it in the lowest possible ratio. I'm actually going to use that word possible. I like that. I need to say that. Lowest possible ratio. Okay. That again is only true for ionics, not for covalents. All right, so in a binary ionic compound, binary of course just means 2. You're only going to have 2 elements. Okay, this is not going to include polyatomics where you have more than 2. They're going to be composed of a metal ion and a non-metal ion, of course, and we are going to have no prefixes. No prefixes are going to be used. So no monos, no dis, no tris, no tetras, no pentas. You guys get the idea, okay? We're not going to use any of those. All right, so let me scroll this up. All right, so we're going to to name them. It says the name of the metal stays the same, so the first element is going to stay the same. Kind of like in covalence when it was carbon. We don't change the first element if it's carbon. In ionic, we also do not change the first element. It's just going to stay the same. But the second element, which is the non-metal anion, is going to end in "ide." Okay, so if we have an atom of oxygen, O, we call that, if it has a -2 charge, we call that oxide. Now, you might be thinking, wait a minute, Mr. Wine, you told me that oxygen is also O2. Okay, that's correct, but careful. O2 is a covalent compound made between two nonmetals, which happen to both be oxygens. They're sharing their electrons in a double bond, and it's a nonpolar covalent bond. So we don't say oxide, that's just oxygen, because if I have oxygen in the air right now, or a tank full of pure oxygen, it is nothing but O2. What we're talking about here is a single oxygen atom with a charge, right? That is what we're talking about, a single oxygen atom that has a charge. Those are called oxides. That is totally different than what I have over here, which is oxygen. That's a covalent compound. Oxide is just a atom of oxygen with a charge of -2. Phosphorus, again, with a -3 charge, because again, it has 5 valence electrons. If you look behind me on the periodic table, there it is right there. So that's phosphorus with a, if it's going to be a charge, it's going to gain 1, 2, 3 more electrons. So it has a -3 charge. We call that phosphide. So oxygen becomes oxide, chlorine becomes chloride, iodine becomes iodide, selenium becomes selenide. You get the idea. Fluoride, nitride, oxide, carbide. Okay, those all going to end in "ide" every single time for the non-metal. Okay, so here is another weird example, a special anion called peroxide. So O2 with a -2 charge is called peroxide. So again, if this right here was not charged, that would be just regular oxygen. But because it is charged, that's called peroxide. You guys heard of hydrogen peroxide, right? So that's just something you guys need to know. So that's something, again, know that. To make an ionic compound, the net charge must always equal 0. All the positives and all the negatives will cancel out, and so there will be no net charge on the covalent compound. All right, so in this examples here, we have a silver chloride. Ag has a +1 charge. Now, silver is located, this is hard, right about there. Again, don't hold me to it, but it's somewhere in that ballpark, which is a transition metal, and I'll talk to you about that in just a moment. But it does have a +1 charge. Chlorine, of course, right there, has a -1 charge. So again, if I was going to write its formula, I would take the two charges and I would crisscross them. That -1 and that +1 becomes AgCl. Not Ag1Cl1, just AgCl. Okay, again, it's redundant and unnecessary to say Ag1Cl1. If you put Cl, clearly there's a chlorine, right? The next example, we have calcium with a +2, and then we have, well, we're going to need 2 bariums because, again, if I move that down, we're going to need 2 barium or bromines. Bromine has a -1, so if I move that down, I'm only going to need 1 calcium. So it's CaBr2. That's calcium bromide, silver chloride. Same thing here. Move that down. I'm going to need 2 chlorines. Move that 1 down. I only need 1 iron. So it is iron 2 chloride. Now, what's up with this? Okay. The reason why we have a Roman numeral is because iron is located somewhere in the D block. It's a transition metal, and their charges change. They could be several different things. So the reason why we have a Roman numeral on iron 2 chloride is because that Roman numeral is telling us what the charge is. Literally, if they do not tell us in a Roman numeral what the charge of iron is, I don't know. I literally, as a teacher, don't know what the charge of aluminum is, iron, unless they tell me what the charge is in this particular compound. Here, it's iron 2 chloride. So I know if I was going to be writing my formula, iron 2 chloride would be Fe plus 2, chlorine minus 1. Again, crisscross. So iron 2 chloride would have to be FeCl2. Again, if it was iron 3 chloride, that'd be FeCl3. But they would have to tell us that because we do not expect you to know what the transition metals are, except two exceptions. One is silver. The other one is zinc. And we'll get to that in just a moment. All right, so let's go ahead and try these really quick. So Na2O, Na2O, Na is sodium. Again, notice it doesn't change the name. It's not sodide or something ugly like that. It's just sodium. And then oxygen becomes oxide. Again, no prefixes. And I'm not referring to those numbers whatsoever. So naming ionics is very easy. Sodium oxide. It's not disodium oxide or disodium monoxide. Nope, it's just sodium oxide. We don't have to say how many sodiums are because we know oxygen has a charge of 2, sodium has a charge of 1, so we need 2 sodiums for every 1 oxygen. We know that. Going over to the right, MgS. MgS, so Mg is magnesium, and S is not sulfur, but sulfide, magnesium sulfide, okay? Again, if you remember, magnesium has a charge of +2, sulfide has a charge of -2. Again, what they've done is they've canceled them out. So therefore, it's just MgS, not Mg2S2. That is not necessary, it's just MgS. All right, the next one, we have Na2O2. Again, that is actually wrong. That does not make any sense whatsoever. That is absolutely incorrect. There we go. That is correct. And it's exactly the same as the one above it. What the heck is up with that? Okay, we're just going to skip that one because that is all wrong. Let's move over to this one. So we have AlN. AlN would be aluminum. And then nitrogen becomes nitride. Okay, again, aluminum would have a +3. Nitrogen has -3. Those cancel out. Therefore, it's just AlN, not Al3N3. It's just AlN. All right, let's go the other direction. So now we have potassium chloride. This is a little bit harder. Potassium chloride. Potassium is K. It has a +1 charge. Chloride is a Cl with a minus charge. Again, if I do the crisscross and move that down there, they're both 1s. So really, I don't need to write anything. It's just going to be KCl. That's potassium chloride, KCl, not K1, Cl1, just KCl. Over here, we have calcium oxide. Calcium is Ca with a +2 charge because it's in the second column. Oxygen is a -2 because it's in the 6th group of the periodic table. Again, same thing again. I could move that down there and move that down there. And again, you might think, okay, so it must be Ca2O2. But remember, we reduce. So it is just CaO. That is calcium oxide, CaO. All right, let's move on to a little bit harder ones. So we have lithium sulfide. Lithium is a +1. Sulfide is a -2. You have to start memorizing these guys. It really helps if you have these memorized. Again, going to move that 2 down here, that 1 down there. So the final answer is going to be lithium 2, sulfide 1, or Li2S. Li2S is lithium sulfide because lithium has 1, sulfur needs 2, so it's going to take 2 lithiums to fill the 1 sulfur. Strontium bromide. Strontium bromide, what we have here is strontium is Sr, is a +2 charge, and bromide is a Br with a -1 charge. So again, I'm going to cross, and what we get is Sr1, Br2. That is strontium bromide, SrBr2. Okay. All right, aluminum oxide, the next one, what we have here is Al and O. Al has a +3 charge, O has a -2 charge. Again, if I cross that down there, what we end up with is Al2O3. That's aluminum oxide, Al2O3, aluminum oxide. Last one, we have barium, which is a +2, and a phosphide or phosphorus with a -3. Okay, again, you guys are noticing the pattern. I'm going to move that down there, that down there. What that does, that gets me Ba3P2. That's barium phosphide. Again, we don't put the numbers in the name like we do with covalence because there is literally only one way that barium phosphide can be formed, and that's of a ratio of 3 to 2 bariums to phosphides. Again, there's only one single way that aluminum and oxygen combined, and that's in a 2 to 3 ratio from 2 aluminums to 3 oxygens. So we don't have to say it because there's really only one possible combination. Whereas in a covalent, when we're putting together different nonmetals, there's many different combinations that they could go in. So we have to distinguish that with our specific prefixes. Again, we don't do that with ionics. Okay? All right, guys, I believe I'm going to stop right there because I think I'm about to get into polyatomics. Oh, no, I'm going to move on. So I'm sorry, guys. That was a false alarm. I'm going to go ahead and keep moving on because I want to make this into one video as opposed to multiple videos, despite the fact it may be a bit long. I do apologize. It says, if the positive ion has more than one oxidation charge, the name of the compound must be stated which oxidation charge is used. Use the elemental name and a Roman numeral, I already kind of touched on this earlier, in the parentheses that tells the oxidation number or the charge. So for example, iron 3 chloride would be iron with a +3 charge, chlorine with a -1. Iron 2 chloride would have to be iron with a +2 charge, and then chlorine with a -1. Okay, again, if I move that down there or move that down there, what we get is, of course, FeCl3 or FeCl2. Okay, so that's why we have to indicate this is iron 2 chloride, this is iron 3 chloride, because that's going to determine this number here as to what was the original charge of our particular iron. Now, the two that you must memorize is silver has a +1 charge. You will never see, silver with anything than a +1. Silver never has a +2 or a +3. And zinc always has a +3, never has anything else. So we don't have to say silver 1 chloride. It's just silver chloride because silver chloride is a 1 silver. So silver chloride would be AgCl. Zinc chloride would be ZnCl3. We don't have to say zinc 3 chloride. It's just zinc chloride, ZnCl3. All right, so let's try these examples real quick. Oops. Okay, that's where we're going to stop. All right, so in this particular case, what we have, again, is copper 1 bromide. Copper is Cu. It tells us the charge is 1. Bromide, of course, is Br with a -1, right? So I didn't leave myself very much space, did I? So Cu1Br1 is what it would come out to be. Or really, I'm just going to put it over here, guys. Sorry about this. CuBr. That's copper 1 bromide. Okay, I'm going to do this a little bit differently this time to make myself a little more space. Copper 2 fluoride. Fluoride's a -1 because it's a halogen, just like bromine. But this time, copper has a charge of 2 because it tells us, versus copper 1 that had a charge of 1. So therefore, when I do my little crisscross, this 2 is going to move down here, this 1's going to move down there, and what we end up with is, of course, not surprisingly, CuF2. That's copper 2 fluoride, whereas over here is copper 1 bromide. Okay, aluminum bromide. Aluminum is Al with a +3 charge. Bromide is Br with a -1. Again, if we just take those charges, drop off the positive, negative, move those down, what we get is AlBr3. Tin 3 bromide. Tin is SN. It tells us the charge of tin is 3. Bromide, of course, is -1. So again, same thing as always. We're going to move that down there, and what we end up with is those numbers crossed, SN1, Br3. That's tin 3 bromide. All right, antimony 5 sulfide. Ooh, antimony is Sb. It tells us it has a +5 charge. Okay, sulfide has a -2 charge. So we're going to go ahead and cross that down here. That goes down there. We drop off the positive and the negative. And what we end up with is Sb2S5. That's antimony 5 sulfide. Lead 4 nitrate. Lead is L or Pb, excuse me, what am I thinking? Pb is lead. That Roman numeral right there is a 4, so that's a +4 charge. Nitride always has a -3 charge. So again, same as always, move that 3 down there, that 4 down there, drop off the positive and negative. What we end up with is Pb3N4. Again, those are not reducible because 3 and 4 are not divisible by each other. Same thing with the antimony 5 sulfide. Those are not reducible. So Sb2S5 and Pb3N4 are the smallest possible ratios. Okay, going the opposite direction. Now we need to go into the name, Fe3F. So Fe is iron. Iron is a transition metal, so we need to say what its charge is. And then fluorine becomes fluoride. Notice the U is before the O, fluoride. So the charge of iron, again, is right here. So that's going to be iron 3 fluoride. Here we have MnS. So Mn is manganese, not magnesium, but manganese. Manganese is a transition metal, so we're going to need a Roman numeral. And then sulfur becomes sulfide. So manganese something sulfide. Now the charge of manganese is right there. I don't see a number, so I assume that's a 1, right? Wrong. That is not true. The reason why that is not correct is because you know sulfur has a charge of -2. If sulfur has a charge of -2 and I don't see a 2 there, then what does that tell you about the charge of manganese? The charge of manganese must also be a +2. It has to be a +2 because if sulfur is a +2, a -2, and manganese is a +2, they cancel out, and you would just end up with MnS. Otherwise, it'd be Mn2S. So that tells me that the charge of manganese must be 2. It's manganese 2 sulfide because it canceled out the charge of the sulfur. PbO, Pb is lead. Lead is a transition metal, and then oxygen becomes oxide. So again, same thing. The charge of the lead should be right here. But again, you know that oxygen is a -2. Since I don't see the -2 here, what is the charge of lead? You guessed it. In this case, it must be lead 2 oxide. All right, in this particular case, we have lead, Roman numeral, oxide. Okay, so this is interesting because there's a 2, right? Well, there wasn't a 2 there, so what's up with that? That's confusing because remember, we already know that oxygen must be 2. And we know that it can be reduced. So what do you think that tells me about the charge of this lead? It's not 1, it's not 2, because otherwise, like here on the left side of your screen, we knew that this had to have been a +2 right there. That's why they canceled out. That's why it just became PbO. But the fact it's PbO2 and the oxygen has 2, that means that this particular lead must be lead 4 oxide. There's no way around it. Lead 4 oxide would reduce let me go ahead and show you, would reduce down to PbO2, right? Once I do the crisscross, it'd be Pb2O4, Pb2O4, or reduce that down to PbO2. So that lead must have a charge of 4. That's the only way the oxygen can have the 2 at the end, okay? All right, guys, this is a super long video. Again, I apologize, but that's everything you need to know about naming binary for ionic compounds. Again, I really appreciate you guys watching that. Thanks again.